Continuing, get the notes up there. So we're dealing with the Laplace transform method for solving differential equations, aren't we? So in previous weeks, we've introduced the transform. We've looked at key properties that the transform has. It's linear. It behaves very well when you take a transform of a derivative of some other function. It's very closely related to the transform of the other function, undifferentiated. So those are the key properties that enable you to transform a differential equation, such as those ones there, and obtain an algebraic equation, still featuring an unknown function, but it's now an algebraic equation, which is easy to solve, easier than the ODE to solve. It's solvable just using relatively straightforward algebraic manipulation. Then in principle, you just take an inverse transform to recover the solution to the original problem. Although that may require a bit of tweaking first, like using partial fraction expansions and a bit of fiddling around to make things look like the standard results in the Laplace transform table, before finally you take the inverse transform to recover the original solution. We also saw examples not just of single isolated ODEs, but systems of two so-called coupled ODEs. So where you've got two unknown functions, these examples are an x and a y, both functions of t, and you've got two equations featuring, two differential equations featuring both of the functions. And the method applies in essentially the same way to these. So what more do we have to do? Well, what we're going to do now is slightly expand the range of functions that we can have in our ODEs. Okay? So it's still going to be the same method that we're using to solve them, but we're just slightly widening our view to take in more types of functions that we can deal with. Okay? So there's two functions we're going to introduce. May or may not have heard of them before. They're called the Dirac delta function and the Heaviside step function. Now we're going to look at the Heaviside step function first of all. Now first of all, there's just a little bit of a kind of motivating kind of example here, which is a differential equation or an integral equation equivalently, which comes from the analysis of an electrical circuit up here. So you've got a resistor, you've got a switch, you've got a power source here, there's a capacitor here, and so on. Now we're not going to delve into electronics or anything, but just to see that, you know, this is another kind of real world situation or engineering type situation out of which comes a differential equation. Okay, so you can see there's the unknown function that's featuring here is the function I. I is traditionally used to denote the current in a circuit. And you've got the function I, you've got a derivative of I, and over here you've got an integral of I. So it's equivalent to a differential equation. You've got different derivatives or integrals of different order of the unknown function I. But now there's at least two different types of electrical circuit you can have. Those would be circuits which are maybe on the one hand driven by a direct current, DC power. So that's where the electrical current is flowing in a certain direction and it's always flowing in that direction. Alternatively, you'll know that you can have electrical circuits which are driven by alternating current. And that's where the current is constantly switching direction. It's constantly flicking from flowing one way through the circuit to flowing the other way circuit. And it typically flicks like, you know, many, many times per second. I'm just trying to, what's the typical AC frequency? I think it's something like the AC that's flowing through your house or flat is typically, anybody know the hertz? Is it like a couple of hundred hertz? Anybody know that? I think it switches direction a couple of hundred times a second, maybe. I could be completely wrong on that, but it's something of that order. It's not thousands of times a second, I don't think. I'm completely speculating, but or misremembered. But anyway, that's alternating current, where the direction of the current is constantly flickering back and forwards. But as well, of course, in electrical circuits, you've got switches. So you have this notion that you can turn on and off the power. And when you have a capacitor in a circuit, a capacitor is something that builds up charge in it and then lets the charge dissipate out of it over a certain period of time. So this is where we see the Heaviside function coming in. We want to be able to represent functions in a neat way, functions that turn on and off. Okay? So for instance, this might be a typical graph of the alternating current. It's 0 most of the time, but for a certain period of time, the switch in the circuit is flicked, and we have the alternating current flowing through the circuit. Or if it's a direct current, well, most of the time the switch is off, but then the switch is turned on for a certain period of time, and so that delivers a certain level of current into the circuit for a certain time. So we want to be able to represent the idea of a function getting switched on and switched off. Okay, so there's this motivating question. How do we represent, or how do we express the idea of functions being turned on and turned off? Well, we do so with what's called the Heaviside step function. So this function introduced in definition 2.2 Heaviside is a person's name. It's an English engineer type mathematician guy. Step up, not step up, got step up in the brain. Heaviside step function. And it's an extremely simple function. I mean, the most simple function you can have is a constant function, like the 0 function which always takes the value 0. Well, this is the next best thing to a simple constant function. It's a function which just takes two different constants. And the constants it takes are extremely simple. The most simple two constants there are 0 and 1. So there's the graph of the function h of t. I think we're generally talking about time here, time starting at 0, or, well, you can even have times, negative times going back into the past, I guess, from some point. So it's a very simple function. The next best thing to having just a plain old constant function, this function takes two constant values, takes the value 0 when t is strictly less than 0, and the value 1 when t is strictly greater than 1. Strictly greater than 0. So when the function is 0, it's a helpful analogy. It's helpful to think of it as the function is switched off. And when it takes the value 1, it's switched on. So that function h is switched off for all times up to time 0. And then for every time after time 0, it's switched on. It takes the value 1. And what we're going to see is how using this function and using combinations of it, expressions built out of the Heaviside step function, we can achieve our aim of more or less representing any function which gets switched on and off over any time interval. Okay? So we don't need a whole suite of different switch functions, if you like. We can just make do with this one and taking appropriate combinations of it. Okay, so we'll talk through that. We'll talk through that now. Okay, the first thing we might want to do is move the point at which the switch happens. Maybe we don't want it switching on at 0. Maybe we want to switch on at some other time. Well, that can be easily achieved still using the same function, but just by performing a shift in the argument. Okay, So if we consider h of t minus a, for some constant a in the real numbers, well, h still has the same definition. So what values will this have? H of t minus a will be 0 when t minus a is less than 0, and 1 when t minus a is greater than or equal to 0. Or in other words, 0 when t is less than a, and 1 when t is greater than or equal to a. So now this version of the Heaviside step function, where we've shifted the argument, it's still being switched off for every time up to a certain point and then switching on, but now the switch is happening at the point A. So you have A, some point here, function is 0, it's just along the horizontal axis everywhere up to A, and then suddenly it jumps to the value 1. It switches on at that point. So that's t, so that green graph there is h of t minus a. The way I've drawn it there suggests a is positive, but you don't have to have a being positive. It could be negative over here. Okay. Any queries about that, or anything you're unsure about? I think it's quite straightforward. So we just keep playing with it. Keep playing with this Heaviside step function. Now consider this thing, example 2.11. How does this kind of thing behave? H of t minus a minus h of t minus b. A lot of what I'm writing down here is already in the notes, and it just helps me to explain it, make it a bit more interesting if I write it out. Well, how is this thing going to behave? I'm assuming here I think that A is less than B. So A and B are just 2 points on the line. How is this thing going to behave? Well, they're both just 2 copies of the Heaviside function that have been shifted, where the argument to it has been shifted by 2 different amounts. So remember, this function here is switched off. It's equal to 0 everywhere to the left of A, and then it's equal to 1 everywhere to the right of A. But the second term is equal to 0 everywhere to the left of B, and then equal to 1 everywhere to the right of B. So if you imagine kind of scanning across the number line from left to right, when you're left of the point A, both functions are 0. So it's just 0 minus 0, 0. However, once you pass A, the first function switches on and takes the value 1, but you're still to the left of B, so the second function is still switched off. So it's 1 minus 0, it's 1. So the function jumps up to the value 1. And that situation is maintained for all of these points here between A and B. But what happens when you pass the point B? Well, you're still to the right of A, so the first function is still taking the value 1. But you suddenly, when you pass B, the second function, which was 0, it now switches on. And it's taking the value 1 as well. But you got 1 minus 1, so you're back to 0. And that situation is maintained forevermore. Okay? So this is nice. This combination gives us a signal or a function which is switched on for some of the time and switched off for the rest of the time. That's good. So we can switch it on at time A, switch it off at time B. So it's equal to 1 in the case where A is less than or equal to T is less than B, and it's 0 otherwise. And to be honest, it's not that crucial how you set things up about what exactly is going on at the end point. I mean, whether the thing is switched off at A or switched on at A, or vice versa at B, because that's just a single instant in time. And we're going to be integrating these things, and integrals don't care what happens at a single point. They're really only measuring what happens over intervals. So, I mean, the way I've set things up, I've set it up, if you look back at the original definition of H, it's off for everything strictly less than 0 and on for everything greater than or equal to 0. You could equally well, you could have had less than or equal to 0 here and strictly greater than or equal to 0 there. So the main thing is just to be consistent. And indeed, other books might have the other thing, you know, have the equality on the other one. But it's not really important, okay, what happens at those specific time points themselves, okay? So we have this nice idea of the signal now, which is switched on some of the time and switched off at all other times. And you can just adjust A and B to get any kind of switching behavior that you want. So in the second example, you'll see, what have we done there? Well, we've stuck with our h of t minus a minus h of t minus b. What have we done now? We've multiplied it by some other function. Now this is just some 1 plus cosine of t. That's just some relatively interesting signal I'm just choosing for this example. Nothing particularly special about it. So what kind of function is this, f of t? Well, when you see this combination of Heavisides, the way you interpret it, as I've said before, we think of it as switched on between A and B, switched on for values of t, the argument between A and B, and switched off otherwise. So it's a switch which takes the values 0 and 1. And it's multiplied by this function. So it's going to have the effect of taking this function here and turning it on and off. Turning it on inside the interval a to b and turning it off outside of that. No. So here's t. I'll try and do something now. My wonderful colors. Let's draw 1, 2. I should do it as black. 1, 2. Cosine of 0 is 1, so this function is what's that function? Why have I drawn that? What's that? That's a green function. What is it? That's the function 1 plus cosine of t. Cosine of t varies between +1 and -1. So you get a familiar cosine signal which varies between 0 and 1. But that's not the function f. The function f is this function, but just switched on between these times a and b. So a and b are somewhere in the picture. Say a is here, b might be up here. So the function f, color will I draw that in? Red. The function f is this graph. So it follows the signal 1 plus cosine of t, but only between the values. Does that come out there? That was pretty good. It follows the signal 1 plus cosine of t, but just between the values of a and b. Outside of that, it takes the value 0. So I'll put a heavy red line down here, a heavy red line down here. So the red graph, 0 most of the time, 0 almost all of the time. But between the values a and b, it suddenly starts to follow that other function there, the 1 plus cosine of t. Everybody's swapping between the different colors as well. I feel sorry for you guys who only have a blue pen or only a black pen. You're deprived. Okay. Is that okay? Does that make sense? So we have the ability now to represent signals that are just switched on over a certain period of time. So this red function here is the function f of t. It's equal to 1 plus cosine of t between a and b and 0 otherwise. Any questions? Okay, so let's have a go together at this question 3. So here's a piece. So when you define a function like this with not a single formula, but different formulas in different situations, it's called a piecewise defined function, or a cases defined function. Different cases for the function values. So here's a function v described there. So what we'd like to do is sketch a graph of v and find a definition for it, a single formula for it, rather than the 3 separate cases, depending on what value t is. Find a single expression for it. Now, how do you do that? How do you gather 0, t, and 2 into one expression? Well, you can do it using the Heaviside function as a switching mechanism, to switch on and off the various parts there at the appropriate times, okay? So let's take a few minutes to work on that. So this is v of t, 0, for t less than 0, takes the value t between 0 and 2. And then it takes the value 2 for everything beyond 2. Okay, so draw the graph of that and then find the expression in terms of Heavisides. I'll show you my page in a moment. And universally, my page will look exactly like your page, because you'll have done it, well, unless I make a mistake. Okay, I've got my graph drawn. And I'll now start to write down the expression for v in terms of Heavisides. So you should be doing the same thing. And to get the final expression, try and collect together all the similar Heaviside functions. So if there's the same Heaviside function in 2 different places in your expression, bring them together. Everybody finished? Another minute? Another 30 seconds? So check your neighbors, see if you got the same thing as your neighbors. Okay, here's the bit we find out where I went wrong, probably. So that's the graph of V, yeah? Does everybody agree with that? 0 to the left of 0. Between 0 and 2, it's the graph of V of t equals t. But then from the point 2 onwards, it just becomes the constant function 2. That's kind of what the graph of V would look like. And it's very obviously, okay, so it's 0 to the left of 0. I think that part takes care of itself, really. It's made up of two sections, the section where it's following the function t and the section where it's following the function 2. So in our expression for v, we're going to want to take the function t and turn it on and turn it off. We'll turn it on just inside the interval 0 to 2. So that's achieved by using this combination, h of t minus h of t minus 2. That's the switch which is switched off everywhere except for between 0 and 2. And it's this function t that we want to switch on between 0 and 2. So if we just had this, that would be this part of the function, but then it would take the value 0 everywhere outside, everywhere after 2, wouldn't it? If it was just this. But that's fine for this part, but then we want it to be the constant value 2 at every value of t bigger than 2, so that's achieved with this. h of t minus 2 is the switch, the Heaviside switch function, step function, which is 0 everywhere to the left of t equals 2, and then is switched on, takes the value 1 everywhere to the right of t equals 2. And when you multiply it by 2, then it bumps up the value 1 up to 2. But you can see the Heaviside t minus 2 is floating around in a couple of places there, so you can bring them together, just collect them together into that kind of expression. Okay? So now we have a, it's really just a notational tool or a notational convenience at this point, really, that can allow us to get away from writing, case-by-case definitions of functions and instead write them as single expressions. Of course, the case-by-case stuff is still buried in there because it's part and parcel of what these functions h are. They're inherently two different types of behavior. Okay. But at least notationally, at least on the page, it allows us to get it down as a single expression that defines the function everywhere. Is that okay? Any questions? Yeah, question. How have I got that? So why is that there? Because this you're talking about this t. Yeah. So that t there, just like in the previous example, the bit that was in front of the Heaviside stuff was the signal that we were trying to pick up. Yeah. Did you see that bit? Well, here, this t is this. So this green t here, that's this part of the graph. That 45-degree line is the graph of the function v of t equals t, f of t equals t. So that's part of v, but only between the values of 0 and 2. So it's this. So this is like playing the role that 1 plus cosine t played here, except it's t. And I'm going to switch that on between, so you can think of this h of t here as being t minus 0, switched on between 0 and 2. Is that okay? Yeah? And then the 2 is playing that role, but just from the point 2 onwards, yeah? Okay, good. Good, good. Okie doke. Let's leave the Dirac delta function for a moment. We'll return to that later, or maybe next week. Yeah. There's some more examples like that V of t example there in exercises 2.3, question 1, question 2 indeed. What I'd like to get on is start talking about the transforms of these functions. So I said at the start we were going to we want to extend our method for solving ODEs to be able to cope with ODEs which feature these switched functions. Well, in order to do that, you see the first step of the Laplace transform solution method is to transform the whole equation. So if there's Heavisides floating around in our equation, in our original ODE, we're going to need to know how to take their transforms. So we've got a couple of theorems here which explain how we do it. And these need proofs. So I said proofs and lectures, yeah, for these. So first of all, let's just look at the theorem 2.4, which is going to tell us what the Laplace transform of just the plain old Heaviside step function on its own is. But then look, we're going to, theorem 2.5, really theorem 2.4 is a special case of theorem 2.5. Theorem 2.5, excuse me, is the fully fledged result, which is going to tell us what the transform of any product is of the form f of t minus a times h of t minus a. And that result, theorem 2.5, using it wisely, that will more or less allow us to take the transform of any combination of Heavisides that we encounter in this unit anyway. So what is the transform of the Heaviside step function? Well, we ought to be able to obtain it because it's a very simple function. It's just 0 and then it's 1. So it's not that complicated a function. And we know what the definition of the Laplace transform is. It's the integral of e to the minus st times h of t dt. Oh, sorry, this is theorem 2. Oh, yeah, I forgot to add in the a minus a. Let's stick in the minus a in a minute. Well, that simplifies, doesn't it, that integral? What is that? I haven't finished. There's a bit missing. What goes inside the integral? T? Not T, no. Cos. Crikey. I don't think so. You were thinking of re-expressing the exponential as cosines and sines? I mean, you could do. Just even simpler. How does h behave? H is either 0 or 1. It's 0 everywhere before 0, and everywhere after 0, it's just 1. But look, in this integral, t is only ever greater than 0, because 0 is the lower limit of the integral. So as far as the integral is concerned, it's just the integral of e to the minus st. Because the h, it's not really some complicated object here. It's just h of t, where t is positive, so therefore it's 1. So it just reduces to integral of e to the minus st. So as far as the integral is concerned, this is just the integral of e to the minus st, and that's immediate. This integrates to e to the minus st over minus s, evaluated at 0, and as t goes to infinity, And this is just equal to 1 over s. Okay. Just as we saw, it was equal to 1 over s. So actually, that's just the same integral as the Laplace transform of the constant function 1. Because between 0 and infinity, that's just what the Heaviside step function is. Okay, so let's do the proper theorem 2.4, where we allow the switch to move to any other location. Okay, with this we can do as well. Yeah, we'll assume that A is, I haven't written there. Yeah, I'll assume that A is positive. So I'll assume A is positive. And if A was negative, this function would just behave just like the h of t, and it would still have the transform 1 over s. Now, what happens here? Remember that the function is still quite simple. It's either 0 or 1. And it's still equal to this. What's the last thing I need to write in? Special kudos if you shout it out. A, where? In the lower limit. So why have we put A there? That's good. T is varying from 0 to infinity. So, but the Heaviside step function, remember, is turned off everywhere before A, for every value of t up to the point A. So for every value of t up to the point A, the integrand, the thing you're integrating, is just 0. So it's got a multiplied by 0 bit. So the integral doesn't get going until t passes the point A. And when t does pass the point A, the Heaviside bit switches on. But it just becomes 1 then. So then it's just the integral of e to the minus st. Okay? So it just reduces to the integral of e to the minus st, but just from the point A. Okay? Because for any value of t earlier than A, the Heaviside factor is 0, so you're just integrating the 0 function, so you don't get any contribution to the integral until you pass t equals A. So that's just from the definition of h of t minus A, which is equal to 0 or 1. But it changes that behavior from 0 to 1 at t equals A. So that's why we have A down here. It's just the integral of an exponential. We can handle that. E to the minus st over minus s. But this time evaluated at, we'll take the limit as t goes to infinity on the top and evaluated at t equals A this time, not t equals 0. So that has the effect of giving this to be minus sa over s. Before we just had 1 over s because we were doing e to the minus s times 0, this lower limit here, and e to the 0 was 1. Whereas this time we're doing e to the minus s t evaluated at t equals A. Okay. Good. Self-correcting students, I like those. So he thought it was minus because, yeah, there's a minus sign there, but then we're subtracting that evaluation, so it's the lower evaluation. Good. Yeah. Please feel free to voice those thoughts, because if you're having the thought, you can bet your dollar that everyone else is having the thought as well. E to the minus sa over s. So that's good. We have a, it's relatively straightforward description of the transform of the Heaviside function. Now, just in time to have our first look at theorem 2.5, although I will return to it at the beginning of next time. Okay. Final burst of concentration. We've got a function f of t minus a times h of t minus a. Now I'll explain, I'll describe, I'll tell you all about why we consider products like this next time. Considering this kind of product is more or less enough to deal with any kind of product featuring the Heaviside step function. Okay, so what is this? Well, we all know what this is. It's a Laplace transform. So it's this kind of integral of the exponential, and the thing you're integrating is the thing you're taking the transform of. So this is f of t minus a times h of t minus a. Yeah? Now I'll move the dt in about this much. Why do I move it in about that much? And why have I left a blank here? Okay. The Heaviside bit is switched off everywhere until t passes a. Everywhere before t passes a, you've got a 0 in here, which is killing the whole integral. So things only start to happen in the integral. Things only start to happen when t passes a. And when it does do, things start to happen because h switches to the value 1. So that gives us f of t minus a here. Now, the thinking is, and when you look at that, and the way to remember this proof, and to be able to reconstruct this proof in an exam, is the thought that this looks almost like the Laplace transform of f of t. That's what you're all thinking. Because it's an integral of the exponential times the function f. And the integral is taken over the infinite range of t. Now, it almost looks like it. There's a couple of things different. The integral is beginning at a, whereas it should be beginning at 0 to be a Laplace transform. And secondly, we're evaluating the function f at t minus a instead of at f of t. So that's a little bit different as well. Yeah, question? Yeah, but the integral from 0 to a is 0. But I like your first thought. What was your first thought? Say it again. Yeah, so we'll carry out this integral by substitution. So that's exactly right. Substitute a new variable for t minus a. du is just equal to dt, because it's just a constant shift between the variables u and t. And also, this here is the limit t equals a. Well, that implies u equals 0, doesn't it? And as t goes to infinity, that implies u goes to infinity. Remember, when you use integration by substitution, you have to substitute the limits of integration as well. So that fixes a lot of things. Integral 0 to infinity, the function f of u du, and it's e to the minus s. Now it's not, see, this was t. Well, if we're changing everything to u, this becomes u plus a. Now this looks even more like a Laplace transform. Integral 0 to infinity, some kind of exponential multiplied by f of u du. Almost a Laplace transform. We just want to get rid of this e to the minus sa bit, but that can just come out to the front. Can't it? Yeah, because, you know, properties of exponents, you just split apart that e to the minus s times u plus a is e to the minus su multiplied by e to the minus sa. But a is a constant. The integral is with respect to u. So that factor e to the minus a has got nothing to do with u. It's independent of u, so you can just float it out to the front of the integral. So these exponentials separate, and this one moves out to the front. So it's e to the minus sa, and what are you looking at there? Now you are looking at the Laplace transform of f. Okay? So it reads the same. Integral of the exponential times f of u du. Now, you're kind of half thinking, well, it's not because it's got a u in it instead of a t, but that is neither here nor there. The t in the definition of the Laplace transform is just the variable of integration. Here it's called u. It's just changing its name from one thing to another. It's still the same integral, yeah? It's just replace t with u. So this is the Laplace transform of the function f of t, f of u, f of whatever. So that's the result of the theorem, is it not? Yeah, except it's called the capital F in the notes. The capital F just stands for the Laplace transform of the original function little f, yeah? Well, no, but that substitution was just to kind of rewrite the integral. Well, no, because I can just do this integral by substitution. I'll just rename u as t. You see, an integral, if I integrate f of x dx, that's just the same as the integral of f of y dy. I know. Well, that was in order to rewrite the original integral. But you know, these things here are just labels. You can call it Fred, or f of Fred d Fred. They're just purely labels. They're just representing the real number, which starts at 0 and goes to infinity. So once you get, so that looks exactly the same. I mean, yeah, okay, you could say that u is equal to t minus a and do the substitution back, but then you just arrive back at this again. You just kind of go in a circle. Well, oh, yeah. Well, really, see, really, I should write these things as the Laplace transform of a function. Mentioning the variable of the function there it's not strictly necessary, and it's strictly kind of shouldn't be done, really. Yeah, because functions are objects in themselves. They don't really depend on what you label the variable as. It's just a label for the argument of the function there. Yeah. Good discussion points there.